In this video, we're going to talk about the origin of pressure in a little more detail. So we discussed where we get the pressure units like 14.7 pounds per square inch. If you imagined a column from sea level all the way to space, and the gas inside that column, on average, because of gravity, it's going down, and it's going to push on whatever's below it. And yes, it gets bounced back up, but if you have one thing falling down and one bouncing up, and they hit, the top one takes back off up, and the bottom one shoots back down and hits the thing below it. And so you, on average, are still taking all the weight of all that gas. Well, that's 14.7 pounds per square inch. So if you hold out your arm, bad hand, boom, there you go. How many square inches do you have on your arm? Holding up a 15-pound weight might not be too hard, but 30, 60, 400, 900? Think about all the square inches on your arm. How are you not instantly crushed under that weight? Realistically, you would be. If you put, 1,000-pound concrete brick on your arm, you just collapse down to the ground right away. If your arm was lying on the ground and you put a 1,000-pound concrete block on it, your arm would get crushed. That's because the concrete is pressing in one specific direction. If you've got some object and you have a weight on it that comes straight down, then it only presses from one side and it can squish the things out the other sides. Think like if you stepped on a piece of fruit, you'd press down from above and the sides would burst out. On the other hand, if you've ever tried to take like a ball and just squish the ball, like a very small ball, and you squish it from all sides, if you're squeezing from all sides, it doesn't really have anywhere to go. At best, you could compress it, but you can't get it to burst open because it can't go out the sides. Something's pressing in on them. This is actually what's happening when you have gases. So I have some object, we'll say this object. And there's gas molecules. They're pressing down on it and they're pushing force in. But have you ever had a stack of kind of circular objects, which is what we think of gas molecules as? Try and build a stack of tennis balls. What's going to happen the moment you let go? Those tennis balls are going to move. They're going to roll off of each other, fall in all directions, and just collapse. They move sideways. Round objects don't stack and stay stacked. They have sideways forces. It's not a principle we'll go into detail, but hydrodynamics, this happens in water, basically says that whatever force you're pressing down on something with, so say this one here, it's getting pressed by all those things above it. Well, it presses down with that force, but it also presses back up and it presses to the sides. Think about standing on, say, a soccer ball. You try to step straight down on a soccer ball and it resists and it resists and it resists. And then suddenly, so you've got your foot pressing down. It resists and resists and then suddenly it just shoots off in one direction. Launches, just flies away. Now, you didn't kick it. You didn't try to push it that direction. It just suddenly shot off. Now, as long as you were perfectly balanced on the ball, it doesn't do it. It's when you kind of go to the side a little and then it rockets off in the direction opposite wherever you started to slide down the side. It was being pressed and trying to push out in all directions. It was resisting being crushed after a little bit. It was being driven down into the earth, but it was also trying to go to the sides. And so the moment your foot shifts a little over, now one direction gets a little bit bigger than the other one, and your ball took off. This is happening with every single gas molecule. Well, when you have a bunch of gas, that means you also have neighboring columns. Net result is, let's look at this one. This is pushing in all directions. And that means the next one is also pushing in all directions, down, sideways, and up. And that's an important point. It's also pushing up, which means the next gas molecule above it, feeling that upward force, also squishes out in all directions. The force is not just straight down. It can travel through any directions. Any pressing down gets spread out in all directions around it. What this means is that if we think of an object and it has a bunch of gas around it, or water, and this is also how water pressure works. Let's imagine a bunch of them around it. Even though you've got your gas coming straight down, just like on the arm, it's pressing sideways into these gases. These gases are pressing in all directions, including down along the side. Well, once you're down further, these are pressing in all directions as well. And so they'll press in, and it means this one is pressing up as well as down into the sides. So this object is not just being pressed from above, it's being pressed from below, and from the left, and from the right. In fact, it's being pressed from all sides equally. So the reason when you have your arm, if you hold it out to your left, right, imagining all these columns of gas pressing down on top, also imagine that just a few inches away from your arm on the side, there's a column that's pressing down until it gets below your arm, presses over until it's under your arm, and presses back up into your lower component of your arm. You are being crushed from all directions equally. This is very different than the large concrete block, which could only crush you from straight down. The concrete didn't roll around you and press in from all sides. Gases can distribute their force over the entirety of the surface of anything that's there. As a result, they are pressed equally from all sides and can only compress, so they don't get squished. You really are bearing an enormous weight of gas, crushing you from all sides. We're just built to handle it. We're filled with water. Water does not compress very well. So as a result, we can't really get squished any more than we are. Our cells have an outward pressure. They're kind of like a balloon, and it matches the inward pressure from the gas. If you dive deep underwater, you do end up getting pressed a little bit more, and so you can get squished a little bit. But water doesn't really compress. Very quickly, it just matches, increases its pressure, and pushes back out. And so humans are actually very resilient to pressure as long as we're allowed a little time to adjust. We can go up and down quite a lot because of the nature of our lack of compressibility. So a little bit of discussion on where pressure is coming from and why this column coming down from space of gas is not just instantly crushing us.